Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept in electrochemistry, and this is the concept of Faraday's law, which is involved in electrochemical stoichiometry. This basically relates to the quantity of charge that is being used and the amount of substance which is being deposited at the cathode, during the process of electrolysis. We're going to see the relationship between this mass, and the concept of equivalent or the equivalence of a substance that we had discussed in one of our videos when we were trying to handle the concept of normality. So for that case, thank you and welcome. So as I've said, today we're going to look at a process in electrolysis, and this basically is going to entail the concept of Faraday's law. Which we're going to see, which basically entails the relationship between the mass of a substance that is involved in electrolysis and the quantity of a charge that is, being involved. Now, as I've said, we're going to see that there's a relationship between the mass of the substance that is produced and the charge. Now, the sample question on the board, which is calculate the mass of a copper that will be deposited at the cathode when 5,000 coulombs pass through copper sulfate solution. This basically entails the concept of electrolysis, which of course we're going to see later. And this is when the electric current is passed through a solution, which is referred to as an electrolyte, that is basically a conducting solution. So in this case, we're going to see that the implication of Faraday's law in this process of electrolysis is very wide, in a sense that this law tries to give a relationship between the number of electrons or the charge in that essence under the relative formula mass. And the law states that this is Faraday's law that relates to electrochemical stoichiometry. It states that the mass of a substance liberated, during electrolysis is proportional to the quantity of electric charge, Q, that is passed through the cell into the equivalent weight of the substance. It's a broader definition, but of course we're going to see that different parts of this specific definition will give us a clue on what the concept of Faraday's law in electrochemical stoichiometry entails. So basically we have said that the law states that the mass of a substance liberated during electrolysis is proportional to the quantity of electric charge. So therefore there's a relationship, electric charge Q, that is passed through the cell and to the equivalent weight of the substance. Now in this case, of course, we have already discussed the concept of electric charge. Of course, mass is conversant with us, but there's a new concept that is being introduced, of course, which is equivalent weight. And this is the concept that we had discussed when we were trying to talk about the topic of volumetric analysis, whereby we were discussing about the concept of normality of a solution. And we said that normality of a solution is the number of equivalents of a solution per liter, the number of equivalents of a solute per liter. And therefore, this gave us the relationship between mass of a substance, which we said you can be able to donate a proton. So in this case, I'm going to just give a shallow information on this, which is going to assist us maybe in case we need to do some calculations, then we are in a position to understand what the term equivalent means. So an equivalent is the mass of a substance that can donate or accept 1 mole of a proton, or just basically the mass of a substance that can donate or accept 1 mole of a proton. H, that is H positive initial for just a proton from acids. This is for acids and bases. So in this case, we are also going to see that this can be given also in an alternative way. Now, in the concept of electrochemical stoichiometry, this can be given in a different way, whereby we are going to define the equivalent as a mass of a substance that can donate or accept 1 electron in a redox reaction. So basically, trying to look at the two concepts for the equivalent that we have talked about. An equivalent is a mass of a substance that can donate or accept 1 mole of a proton for acids and bases, or alternatively, mass of a substance that can donate or accept 1 electron in a redox reaction. So we're going to see the half equations that we have been presenting for the redox reactions, and try to see how this concept of an equivalent can be employed. So therefore, we came up with the concept of an equivalent from basically the concept of Faraday's law, which states that of course the mass of a substance liberated during electrolysis is proportional to the quantity of electric charge Q that passed through the cell and to the equivalent weight of a substance. So therefore, that is where the concept of an equivalent stems from. Now, suppose I can just do a small illustration for a case here. The equivalent of HCl is equals, so the relative formula mass for HCl is 1 for hydrogen plus 35.5, that is grams for chlorine. This is hydrogen chlorine. So therefore, the relative formula mass is 36.5 grams. So if you try to do I'm just trying to form this HCl using the ions, which of course I'm just using an hazard, just a general illustration for us to try and indicate how something can be able to accept a proton. So in this case, this mass, relative formula mass for HCl that is able to donate a proton, or maybe reversibly we can write it as HCl, H positive plus Cl in solution form. So this is able to donate a proton, and this still has got the mass of 36.5. So this mass is referred to as the equivalent, 1 equivalent of HCl. So therefore, the mass that is able to donate 1 proton is 1 equivalent of that particular mass. So for the case of an acid that consists of maybe 2 protons, like sulfuric acid, this is going to be, so that one. So therefore, we know that this is 2, the relative, I'm trying to find the relative formula mass for this sulfides, 2, so this is 2 plus 32, plus this is 16 by 4, 64. So this is 34 plus 64, this is 98. So if you try to look at this, the relative formula mass for this H sulfuric acid is 98, but in this case it's able to donate 2 electrons. So for us to find an equivalent mass for sulfuric acid, it's going to be 98 divided by 2 electrons, 2 protons, to find the mass equivalent for 1 proton. So therefore, we can say the equivalent of sulfuric acid is 49 grams of the acid is equals to 1 equivalent. So I hope that we have understood the concept of equivalent from Faraday's law. Therefore, we'll just go ahead and try to mention another concept that's going to assist us in trying to solve that. So from the definition of Faraday's law, therefore we can try to look at some of the ways in which we can be able to understand this process of electrolysis. Since our question entails electrolysis, just going to have an illustration for that. So this is so whenever we're trying to have an electrolysis, or we're having an electrolysis process, we have this specific illustration, and we have said this process is taking place under or in a solution of copper sulfate. So this solution, we refer to it as an electrolyte. And basically an electrolyte is a conducting solution that we use in this specific experiment. Now for the, the positive part, or the positive side, we call this one the anode, while the negative plate, we call it the cathode. And in this case, we're going to see that in this particular solution of copper sulfate solution, which is aqueous, it consists of a number of ions. Now that it's an ionic solution that is conducting electricity. So therefore we have in aqueous solution, it has got H positive, copper, 2 positive ions. And then for the negative ion, it has got hydroxide ions. And then we've got the sulfate ions. So these different species of ions are going to, of course, dictate how the process of electrolysis is going to take place. In a sense that, of course, it's going to employ the concept of reactivity series that we have discussed in our previous video, and of course, an introduction to electrochemistry. So in this case, we're going to see that they are also going to have different prevalences depending on its position in the reactivity series for the positive and negative ions, respectively. So from the laws of attraction, we know that the negative opposite charges attract. So therefore, we are going to have at the positive plate, the negative plate, they're going to attract respective opposite charges. Now for the positive plate, it's going to attract the hydroxide ions and the sulfate ions. And then for the positive, for the negative plate, it's going to attract the H plus ions and the copper ions. And of course, we're going to see that from the reactivity series, hydrogen is higher in the reactivity compared to copper. So therefore, copper is likely to be, so the lower the reactivity the metal is, the likelihood of it being reduced. So therefore, copper is going to be deposited on the anode, on the cathode plate, and then hydrogen, of course, we have said it's much more stable, so it's not going to be deposited. So therefore, copper is going to be deposited now that it's lower in the reactivity series. Now, respectively, on the positive plate, we are going to see that there's going to be formation of oxygen gas, which of course results from the reduction of the hydroxide ions, which are going to lose, of course, electrons. So just write that. So the hydroxide ions are going to lose electrons in order to form water plus oxygen gas, and this is of course is trying to balance this for 2, then that is for 2. Okay, this is going to be 4 electrons. So this in this case, this reaction that is going to take place at the anode, therefore the liberation of oxygen gas, whereas copper will be deposited on the negative plate due to the concept or due to the factor of reactivity series that I've mentioned in that particular case. So compound integrals, I think, are going to give us a clue on how we can be able to solve our problem that entails the concept of electrolysis. So whenever I say calculate the mass of copper that is deposited at the cathode when this number of coulombs pass through copper sulfate, this entails the concept of equivalent mass that we have discussed, and also which kind of ion is going to be deposited depending on the preference, as I've said, of these specific ions which are going to be deposited according to the order of reactivity in the reactivity series. So now, therefore, we can just have a look at our question and try to see what is required of us. So therefore, calculate the mass of copper that will be deposited at the cathode when 5,000 coulombs pass through copper sulfate solutions. So in our case, we're going to see that it's copper which is being reduced from copper ions to copper metal. So in this case, that is the half equation that is going to be used. Now in this case, because we have talked about the electrons being equivalent to the mass or the charge, the electrons are going to affect the amount of charge that is being used. We'll have to cater for the number of electrons, of course, which we have talked about, the weight and equivalent weight that is being used to form the product. So 1 mole of ions use 2 moles of electrons to form 1 mole of copper. This is solid aqueous. So therefore the mole ratio is going to be very important. So 1 mole of copper is deposited by 2 moles of electrons. So the relationship therefore is going to be in terms of charge. We are going to have, we said that 1 mole of electron consists of 1 Faraday of charge, which was 96.96485 coulombs. For 2 electrons, it's going to be 96.485 for 1 mole times 2 moles, which have been used here. So that will be the total charge. So therefore, this one is used to deposit 63.5 grams. This is the atomic mass for copper, which basically is 1 mole of copper. From our half equation, 1 mole of copper is the one that is deposited. So for this 1 mole of copper, which has an atomic weight of 60, or mass of 63.5 grams, is being deposited by this number of uses this number of electrons, or the total charge. So if 5,000 coulombs were being used in this particular case, therefore we just have 5,000 coulombs of charge can be able to deposit what amount of mass. So we just do a cross multiplication for this. This is 5,000 coulombs times 63.5 divided by 2 times 96.8. This is 485, which is going to give us 1.65 grams of copper. So 1.65 grams of copper will be deposited at the cathode. So that is how we're going to use that specific approaches, and consequently we can be able still to define this in terms of mass by finding the fraction of this for 1 mole of copper. So this is 1.65 over this one per mole. So we are being requested to find that specific amount of mass. Therefore, that is going to form our end of our discussion for today. And I hope that we have understood the concept of Faraday's law and its implications on such a kind of questions that we have had on the board. So that is it for today, guys. Bye. God bless.